Hello student, welcome to your chemistry lab. Today I am discussing the reaction mechanism of organic chemistry. Today I am discussing substitution reaction and nucleophilic substitution reaction, that is SN1 reaction. Means today I am discussing SN1 reaction. I think in previous video, that is SN2 reaction, all points are clear, so SN1 reaction will be also clear. So watch this, and so now watching the whiteboard. SN1 reaction, substitution nucleophilic unimolecular reaction. Here tertiary alkyl halide and secondary alkyl halide undergo nucleophilic substitution reaction via SN1 mechanism. We know that SN2 reaction is prepared for 1 degree halide and SN1 reaction is prepared for tertiary and secondary alkyl halide. So their reaction with nucleophile are unimolecular. Here given example CH3 plus OH negative gives CH3 OH and Br negative. Here CH3 is tertiary alkyl halide or tertiary bromide. Here rate directly proportional to concentration of alkyl halide. Here CH3 Br. Rate of this reaction depend only on the concentration of substrate and independent of concentration or strength of nucleophile. Whether air concentrated or dilute nucleophile is used makes no difference in the rate. Similarly, strength of the nucleophile also does not have any influence on the rate of SN1 reaction. And next, accordingly, a mechanism in which only the substrate is involved in the rate determining step is proposed, that is SN1 reaction. It is two-step mechanism. First, substrate ionize and form a intermediate carbocation, and it is the rate determining step. As only substrate is involved, it is a unimolecular reaction. As a nucleophile is not involved in this stage, neither its strength nor concentration influence the rate of SN1 reaction. Mechanism is here first CH3 Cl, that is the tertiary alkyl halide. Here Cl bond is break because CH3 are plus I effect, means electron donate the carbon atom, and electron density of carbon is high and carbon is partially negatively charged and Cl also negatively charged, so CCl bond is weak, so CCl bond is break, and this step is slow and this step is rate determining step and form carbocation, 3 degree carbocation. We know that the 3 degree carbocation is more stable due to presence of plus I effect of methyl group. So next step, OH negative, that is the nucleophile, attack in both sides, front side and back side, and product form 100%, 50% retention product and 50% inversion product. Thus the leaving group leaves first and intermediate carbocation is formed. The nucleophile gets connected to it in the second stage, which is first. Stereochemistry of SN1 reaction. To understand the stereochemistry of the SN1 reaction, we must examine the geometry of carbocation intermediate. Here carbocation, that is sp2 hybridized, means trigonal planar, and given structure is so vacant p orbital also present, and we know that a carbocation with 3 groups around C is sp2 hybridized trigonal planar and contain vacant p orbital extended above and below the plane. And next, to illustrate the consequence of having a trigonal planar carbocation form as a reactive intermediate, we examine SN1 reaction of 3-degree alkyl halide A having a leaving group bonded to a stereogenic center. So this reaction here, Br is leaving group, and we see that first step 1 is slow and form carbocation, and nucleophile attack in form front side and back side. Front side attack from B and back side attack from C. Loss of the leaving group in step 1 generate a planar carbocation that is now a achiral. Attack of the nucleophile in step 2 can occur from either the front or back to afford the two products B and C, and these two products are different compound containing one stereogenic center, that is the chiral center. B and C are stereoisomer that are not superimposable, they are enantiomer because there is no preference for nucleophilic attack from either direction, and equal amount of two enantiomer is formed, a racemic mixture. We say that the racemization has occurred. Racemization is the formation of equal amount of two enantiomeric product from single starting material. SN1 reaction proceed with racemization at a single stereogenic center. Two examples are given, two examples of racemization in the SN1 reaction, and first one from racemic mixture and second one also from a racemic mixture. And next, energy diagram for the reaction of SN1 is shown in figure. Each step has own energy barrier with a transition state at each energy maximum, because the transition state for step 1 is at higher energy. Step 1 is rate determining step. Del H 0 for step 1 has positive value because only bond breaking occur, whereas del H 0 of step 2 has negative value because here bond making occurs. The overall reaction is assumed to be exothermic. So final product drawn in at lower energy than initial starting material. And diagram is transition state 1 and transition state 2. EA is activation energy and intermediate step, and del H first step del H is positive and second step del H is negative, and overall is exothermic reaction. So next, reactivity of SN1 reaction. Any factor which increase the stability of intermediate carbocation increase the rate of SN1 reaction. So presence of electron releasing group, that is the plus IFA group, increase the rate of SN1 reaction. Any factor which decrease the stability of carbocation decrease the rate of SN1 reaction. So presence of withdrawing group, that is minus IFA group, decrease the rate of SN1 reaction, and given order are below. CH3Cl is 1 degree, less than CH3CH2Cl, less than CH3CH2Cl, and less than 2-chloropropane, that is the 2 degree, and less than 3 degree. As a size of alkyl group increases, rate of SN1 reaction increases. And next point, in this example, in first one, minus I effect of CCl3 increase the positive charge of the carbocation, stability decreases, so rate of SN1 is decreases. And plus I effect, that is CH3, the plus I effect of methyl group decrease the positive charge of the carbocation and stability increases, so rate of SN1 reaction increases. Following reactivity order are given, and first one is plus M effect stabilize the carbocation, is more reactive. Next, hyperconjugation, and next is no conjugation, and last one is minus I effect of Cl, decrease the stability of carbocation, and last one minus M effect and minus I effect both destabilize the carbocation. So first one is more reactive. Stability of intermediate carbocation gradually decreases, rate of SN1 reaction decreases. And next, solvent effect on rate of SN1 reaction. Polar protic solvent are more favorable for SN1 reaction. We know that polar aprotic solvent for SN2 reaction is more favorable. Here polar protic solvent are more favorable for SN1 reaction. They occupy the space between insufficient carbocation and just leaving group and prevent them for recombining during ionization, that is rate determining step. And here given reaction are shown, and here H2 prevent the leaving group, that is Cl negative, and prevent the leaving group for recombining, that is C positive and Cl negative, and H2O are present in between C positive and Cl negative. So nucleophile, that is Cl negative, to prevent them from recombining. So next, the nucleophile can attack the carbocation from top or bottom side. Thus the polar protic solvent encourages the ionization of substrate and increases rate of formation, that is acetone, alcohol and water. Rate of SN1 reaction gradually increases as dielectric constant of solvent increases. Dielectric constant of solvent is its ability to encourage ionization of solute. As it increases, rate of SN1 reaction increases. Order is H2O greater than acid, formic acid greater than methanol greater than ethanol. And next, effect of substrate. Presence of double bond in beta position increase the stability of carbocation and thereby increase the rate of SN1 reaction. Here first reaction, here it is the allylic bromide, that is CC double bond is present, and first form allylic carbocation which is stable through resonating structure, here show that. And next, here benzyl bromide, here form a benzylic carbocation, here it is stable through resonating structure, and showing this as the intermediate carbocation are stabilized by resonance, they are more easily formed and they compound, forming them become more reactive towards the SN1 reaction. As a here more stable intermediate step are preferred for more stable product. So SN1 reaction intermediate step is carbocation, so more stable carbocation are formed more stable or more preferable for SN1 reaction. So next, in presence of carbonyl group or any withdrawing group, decrease the stability of carbocation by increasing the positively charged, so rate of SN1 reaction decreases. So here CH3CO is, that is CO group is carbonyl group, that is the minus I effect is less reactive than this compound tertiary halide. And next, benzyl chloride and allyl chloride involved in both SN1 and SN2 mechanism. If the solvent is polar aprotic, they interact via SN2 mechanism, and if the solvent is polar protic, the mechanism is shift to SN1 reaction. So next, rearrangement and ring expansion in SN1 reaction. During the course of SN1 reaction, rearrangement and ring expansion take place. If the rearranged carbocation is more stable than initial form of carbocation. This is possible due to alpha hydride or alpha alkyl group shift, that is 1 to hydride shift or 1 to methyl shift, and given example are below. In this example, we are see that B are replaced by OH and form this product. You think it is a right product? No. Here major product is this. That is the major product. Why? Now explain through mechanism. Mechanism is first Br leaves that form a carbocation. It is a 2-degree carbocation. Here hydrogen, and showing this arrow, this hydrogen is 1 to hydride shift form a 3-degree carbocation. We know that in a compound, in this compound 3-degree carbocation is present or 3-degree carbocation is have, so it converted to 2-degree carbocation to 3-degree carbocation. Only carbocation are rearrangement, not free radical are rearrangement. Here 3-degree carbocation is more stable. Next OH negative, that is nucleophile, attack that point and form this product, that is the major product. Clear this? And next similar example, this here major product is this, and explain with mechanism. Here first chlorine is leave out and form 2-degree carbocation, and methyl group is shift from 3-degree carbocation. We know that the 3-degree carbocation is more stable. Next nucleophile OH negative attack that point, form a major product. And next here ring expansion is performed. Here first in this example Br leaves from 3-degree carbocation. We know that the 4-member and 5-member ring, 5-member ring have less or small ring strength, so relieve the ring strength from 4-member to 5-member, and so 4-member converted to 5-member ring, form a 2-degree carbocation. Next methyl group is shift from a 3-degree carbocation. Next OH negative attack to this point, form that product, that is 4-member to 5-member are ring expansion. Ring expansion gives relief from the angle strain and the product becomes more stable. So next allylic rearrangement, when the allylic carbocation is not symmetrical, two products are formed. So first example, and this compound first Br negative are leaves from carbocation, and 2 carbocation are stable through resonating structure, and 2 resonating structure form 2 product. One is major and one is minor. So in such case stability of the product taken into account to decide major product, means more stable carbocation form major product. So next relative rates of some compound towards SN1 reaction. Here 3-degree alkyl halide is more reactive. Next benzylic, next allylic, next 3-degree, next 1-degree. And also same, we here bromine is present, so ordered this. So next, and this example also same, first one is 3-degree and propyl, cyclic propyl group is present. Second one is benzylic, here 3 benzene ring is present and 15 resonating structure are formed, and next one is 2 benzene ring is present and 10 resonating structure are formed, and next CH3COCl, CH3CCl 3-degree, and next benzylic, next allylic. So next effect of nucleophile. Nucleophilicity has no effect on the rate of SN1 reaction, as it is not involved in the rate determining step. So nucleophile have no effect for SN1 reaction. And effect of leaving group. Rate of SN1 reaction depends on the nature of leaving group. If the leaving group is better leaving group, rate increases. It was already discussed in SN2 reaction, same as the case also here. So thank you. I think you are enjoying to watch my video. I think you are understanding the SN1 reaction and also clear all the points, and if are not clear, so comment me and I will be reply to you. Now I will be coming with next part of reaction mechanism of organic chemistry. So thank you everyone. Bye bye.